guys! Okay, oh no! Ah! To be able to exhibit our understanding of Riemann sums and integration and velocity time graphs and how the integral of velocity time graph equals distance.
Okay, so we used Fabian's watch, which collects data for speed and heart rate, among other things, but we used the velocity time graph, and we modeled that function using the data points that the watch gave us. And we modeled the function, which looks like this for me. And then we integrated that using a calculator. And we're going to compare that to the actual distance and see how accurate our data is and how accurate our integration is.
7658, Michael used like natural porn. So we don't have a video camera at the moment, so we're going to use this. I'm really excited for this.
Yeah.
You ready to go?
I'm ready.
Alright.
So after we analyzed the graph, we found out that from time interval 9 minute 58 seconds to 12 minute 26 seconds is easier to analyze, and the graph made a lot of sense during that time interval. So we decided to closely analyze that part of the data.
So right now, the three of us have each picked a different section of the section of the graph that we chose, and we're each working on creating either an equation or multiple equations for the section we're working on, and then from there we can use the sections that we've made to do some integration.
Okay, so this is what the graph is supposed to look like. It's the time speed graph. So I am using these points and slope to get an equation to model the graph. And yeah, that's what I'm working on right now.
How did you combine all the equations, all the stepwise equations? Did you combine all of them?
For this?
Yes.
This isn't from my model equation. This is from just the data points.
Okay.
Yeah. So that part should be in the video.
How do you plan to do your model equation?
Well, I'm going to use the points and slope and put it in point-slope form, and that's going to give me the equation.
Okay, but like, that's a good question. Like, the thing that we learn, the thing that we gonna get is only those small functions.
Yeah.
So how can we gonna combine those functions and make
It's
it
going to be
big?
like a piecewise function.
Oh, so it's like,
like
oh, and put some like limit and say, oh, like 1 to 0. I mean, 1 to 2 is this function, and 2 to 3.
Bam, calculus.
Bam, calculus.
KJ gave me a specific mission to do Riemann sum of the total distance traveled by Fabian from 9:58 to 12:26. So after I calculated out the seconds, I decided to divide the Riemann sum into 6 different intervals, 24.66 seconds apart. And here is my graph. So at 9:58, Fabian's velocity was 6.1 miles per hour, and 10:23, 6, 48, 5.2, and 13, 4.9, 11:38, 5.2, 12:01.
I splitted the entire graph to section 1 to 11, and I found the each graph function. So to find the functions, I found the slopes first. So those are the slopes that I got. And the way that I got slope is just, those are the coordinates that I have, x, y, x1, y1. So basically x1 minus x over y1 minus y, which is -6. Same way. And with those slopes, I found the function. I used y equals ax plus b, and I plug in my slope that I got. Like here, section 1, I got -6. And I plug in -6 here, and then I plug in the coordinate, one of the coordinates that I have to find b. I found b, and it's -0.35. So y equals -6x minus 0.35. But I had to show my limit because this function is only for section 1. So my limit is 1142 to y. I mean from 1142 to 1147. Yeah, same way. I use the same way for every sections. I mean here for every sections. This. So my final function for entire graph is like this: y equals the function that I have, and then the limit function that I have.
You see, I raise a toast to all of us who are breaking our backs every day.
Calculated by Michael Yu. And we have n equals 6. So we have 6 intervals, and the left-hand Riemann sum equals 0.22 miles. And over here we have the right-hand and trapezoid rule calculations. The right-hand sum equals 0.211 miles, and the trapezoid rule is 0.2155 miles. So these are all pretty good approximations because the actual value is 0.21 miles. So the right-hand sum was the closest, and the left-hand sum was a little bit over, but they were all very close, which is good.
I made a mistake. I didn't convert the time to decimal. So, and I got really weird number. I got negative number for integration, which it does not make any sense. So Hannah and KJ helped me to find the right answer.
Freedom ring, well, something on the surface it stinks. I see something on the surface, well, it kinda makes me nervous. Who say that you deserve this, and what kind of God would serve this? We will cure this dirty old disease. Well, if you got the poison, I've got the remedy. The remedy is the experience. This is a dangerous liaison. Us is the comedy. Is that a serious? This is a stranger. No.
17.8515.
That's B.
No, yeah, that's B.
So shine the light on all of your friends. Well, it all amounts to nothing in the end.
So to integrate the function, to integrate the model we made, we put in the function to y1 on our calculator, and then we went to second calc 7, which is the integration, and we put in our lower limits. In this case, it was 12.43, and our upper limit was 12.62. And that gave us the integral for this section of the graph, which was 0.89. And we did that for each section of the graph that we modeled and added them together, which gave us our final integral.
We divided the entire graph to 3 sections: KJ's section, Hannah's section, and my section. And this is the KJ section, and she divided her section's graph to little sections. And we converted this time to decimals by dividing 60, and then we found each section slope, and we found the function.
Stepwise function.
Yeah, that's piecewise function. So, and we indicate those limits, and then we integrate it. So KJ's area is 0.06 and Hannah's area is 0.104 and my area is 0.086, so total area is 0.25, which is 0.04 is off.
When I'm making up my mind, you can turn off the sun, but I'm still